So, I'm a grad student working under the supervision of Dr. Jamie Forrest. Today, I will be talking on characterization of stable polystyrene glass films. So, what is a glass and how glasses are formed? When a liquid is cooled below its melting point and it avoids crystallization, it enters a supercooled liquid regime where the molecular motion slows down. The molecular motion becomes so slow that it falls out of the equilibrium, and the material is appear to be frozen in a laboratory time frame. And the resulting material is a glass. If we look at the curve, we can see that at Tg, the rate of change of volume has significantly changed, and the temperature at this point is known as a glass transition temperature, following the curve one. If we look at the curve two, we if one could cool the liquid at a slower rate as compared to the curve one will get a more dense and more stable glass. So why we are interested in studying the glasses? So Cosme realized that if one could cool the liquid at slower rate, one could go all the way down to the temperature where the entropy of the supercooled liquid line will be equal to the entropy of the crystal. Before that happens, uh, a glass transition intervene, and the glass form at that point is known as an ideal glass. So when we are talking about the glasses, it's important to talk about the physical aging. So physical aging is the slow and gradual rearrangement of the molecules to get the equilibrium state. So recently, a more convenient way of forming the glass has been introduced, which is a physical vapor deposition. The glasses formed this way are more denser and more stable as compared to the glasses formed with the with the cooling of a liquid. So if we look at the curve at the bottom, and the curve at the bottom refers to the rate of change of thickness for the as deposited glass, the glass deposited with the help of PVD, and this is known as a stable glass. While if we look at the and once it at the like once it reaches to the T onset, it's an ordinary glass now. And the we at the top curve refers to the ordinary the sorry once when we are when a stable class is stated, and once it reaches to the onset temperature, the glass is no more a stable glass, it's become an ordinary glass. And we can see that there is a big difference between the thickness for the ordinary glass and its stable glass. So because I will be talking about the difference of the TF and the TG. So TF is the point where the liquid cool line of the ordinary glass meets the stable glass line. Because in the so AFM is like high resolution scanning probe technique, which is capable of imaging the topography as well as studying the material properties of the material at a nanometer scales. And it is also capable of measuring the force versus different distance curve. In next few slides, I will be talking on the measurements taken with the help of force curve. So to discuss a little bit about the force curve is important. So once when at the point A, the tip is moving close towards the surface. At the point B, at a certain distance, at the point B, there is a force of traction between the tip and the sample, and it just snapped into the sample. This the probe is still moving toward the sample. It's and at certain distance, the tip feels a force of repulsion between the sample and the tip. Now, now we are following the curve, the blue curve. In that case, the tip is trying to get off the sample, and at the point P, it finally get rid of the sample and move upward, move back. So So what was the strategy? The strategy was to make the stable glasses with the help of physical vapor deposition, performing the force curve analysis with the help of AFM technique, and then fitting it with the help of DMT model to extract the Young modulus. And what we studied is the modulus as a function of stability and modulus as a function of rejuvenation. So here I just like put the model or the equation for the DMT equation for fitting and finding the modulus of the material, and we use the retract curve and this portion to fit and find the modulus of the material. So first, our first aim was to study the modulus of the material as a function of stability. When I say stability, it means that the difference between the TG and TF. If the difference between TG and TF is higher, it means that it's more stable than the other, which has a difference between TG and TF smaller. So the strategy was to, so in that case, I took like two micron cross 2 micron scan size, and in that area, 216 cron 216 force curve, and then the force curve were fitting with the help of DMT model that I showed. So I've just shown one of the force curve and the fitting with the help of DMT. Here is the distribution of the modulus for 216 cross 216 points at a 2 micron by 2 micron area. So, so we took 5 different stabilities and studied their modulus. So we found that when we are increasing, when the difference between TG and TF is increasing, which means that we are increasing the stability. We see that the modulus increases as a function of stability. So the second part was to find the modulus as a function of rejuvenation. So what does a rejuvenation mean? It is the opposite of the physical aging. What is so for the rejuvenation, we heat the sample, a stable sample, and it slowly and gradually forms an ordinary glass. It transforms into an ordinary glass. So when I say we have studied 0 to 100% rejuvenated film. So what does this say when I say 20% rejuvenated film? It means that the top 20% is the ordinary one, while the rest of the 80% is still the stable film. And the 100% rejuvenated film means that the whole film is now the ordinary film. So we studied that when we are increasing the rejuvenated part or the ordinary part, uh, the modulus of the film decreases. So when we increase the rejuvenation percentage of the film, the modulus of the film decreases. So in conclusion, we had formed like stable glasses. We found that if we are increasing the stability, the modulus or elastic modulus of the film is increasing. While if we are increasing the rejuvenation percentage of the film, the modulus of the film decreases. Thank you.
Take 5 minutes per question. I have a question.
Yeah.
Thank you so much. It was a very insightful presentation. I'm wondering how you obtained the Young's modulus for each sample,
We
unless I missed it.
because okay, if like we had okay, with the help of AFM, we were able to perform the force curve. For instance, for one stability, we took almost 2 3 different scans of two micron by 2 micron area, and then like in that 2 micron by 2 micron area, we collected 216 cross 216 force curve. Then fitting the force curve, okay, then fitted the force curve with the help of the DMT model and
Okay.
plotted the distribution.
Okay,
And
that's it. Thank you. Clarifying question.
What quantity do you look for or measure that indicates that a glass has physically aged to a stable glass?
okay, um, For that one, like we can measure TF, like the effective temperature. So like for instance, for instance I made the sample. I have two different films for the same sample. I made the TF and TG for the like the freshly made sample, and we for instance the difference between that is 10 Kelvin. Now after some time, or like after like few days, or with the temperature, I'm not, I'm again going to measure the TF and TG for the other film I had of the same sample. Now, the difference between them will, we will see that there is the difference between them will decrease. And that's how we know that it has physically aged.
The presentation. Uh, I'm in engineering, so I like applications. I was kind of curious, what are the applications for?
So, okay.
for-
So for this one, like, okay, this can be used like photovoltaic cells, yes, and then like fiber glasses, normal glasses, and this like, and almost the, and one important thing is like almost a huge amount of water in Earth is also in the form of the glass. Sure, yeah. So we are. Uh, if the glass transition temperature of that material is higher than the glass transition, like normal temperature, room temperature, then it will stay in the like glass, like it will stay as a glass. Like once the temperature of the environment reaches the TG of that sample, then it will form the liquid. So that's why the scientists are afraid of the water, because if someday the temperature is near the TG of that water, and then we will have like floods and everything around.
follow-
Yeah.
Um,
Yeah.
I wonder, like now you've kind of characterized the material properties
Yeah.
of the glass over stability. What's
Yeah.
kind of like the next steps? Like, what do you plan to work on this a little more?
Okay, no, for like because okay, uh that was like one part of my project. The another one is to find the dielectric properties of the PMA. But for this one, like it's okay, because we found that the samples we have like made with the help of physical vapor deposition at our lab is as stable as the one collected from the moon. So they found the different, like um they found the like they had the sample, they found the material, like they found the modulus for that sample, and they know that the what is the like how long they have been there to have a age, how aged that samples are, and the difference between like this were almost equivalent to ours. So
You know,
yeah, yeah, but there was a talk, and my professor went in and he said that our material is as strong as like the one that's, I think, yeah.
Yeah, my question was that when you were looking into these samples, what would you
Yeah.
say is like, what were the criteria for you to say that this superimposed class is like suitable for like applications?
Applications. So okay. So for normally, because okay, not I'm not like a physics. I'm a physics student. I'm not like very much into the application, but I feel like, for instance, if an ordinary glass, for instance, if I have an ordinary polystyrene, I was working on polystyrene, and then like it has almost like two, like the normal polystyrene, it's some, the modulus is around, sometimes it's GPA, or like gigapascal, sometimes it's megapascal for the one with like small molecular weight. So once we like with the help, we saw that the stable glasses of the same PMA, sorry, polystyrene, it has the modulus in gigapascal range. So that's why we are saying that like it has a higher modulus as compared to the ordinary ones. So yeah. Yeah, maybe, yeah. Mm, there are not much work on the application things for this one, because there's any kind of thing.